Let me continue the part 2 of design of doubly reinforced beam. Let us check the procedure of design of beam. The last one we have done the analysis. Here given mu and we have to find ASC and AST, area of steel in the compression side, area of steel in the tensor side. So, what are the steps? Find mu1 equal to say mu lim, the limiting moment, that balanced moment. We can further write down, or mu1 equal to k FCK BD square. You can check with the last that note. Number 2, calculate AST1 from the expression for balanced section. That also you check it, we have already written explicitly in detail in the analysis of beam. Number 3, mu1 if it is say greater than mu1 if it is greater than mu, that means we do not go, we need to go for design of doubly reinforced section. It is a singly reinforced section. We have to check mu2 equal to mu minus mu1. We can write down the next page, I think. Number 4, calculate AST2 for mu2. AST2 equal to mu2 divided by 0.87 Fy and the lever arm d minus d dash. Okay. For your reference, again we are taking the section and d minus d dash. AST2 means a total area of steel that you are providing. Out of that you have one portion due to your balanced section. So, a section, this section I can make it as in, let us say, equal to, this is equal, I can consider a section of same width and depth, but having only tensile reinforcement here. Let us say this is as AST1, and in this case we are not considering the concrete concrete anymore, we are taking only the steel part, ASC and AST2. Where from you are getting AST1? AST1 is nothing but that balanced section. Due to balanced section, whatever reinforcement you are getting, computing, that is AST1. And why ASC and AST2 different, I have already told, because the stress at this level is different and stress at this level different. And since it has to be in equilibrium, this is in equilibrium. because your compression and tension in equilibrium, and again what you are doing, slowly you are adding reinforcement here and reinforcement here. The reinforcement will different because of your say stress level. So reinforcement area different, but forces are equal, and this is your AST2. So that's why AST2 equal to mu2, the balanced remaining your moment of resistance, remaining moment, divided by 0.87 Fy d minus d dash. Okay. We can find out the total steel area. AST equal to AST1 plus AST2. Number 6, find stress in compression steel. Let us say that is FSC. We can find the FSC. How shall find out? This is at a distance d dash. This is 0.0035. We can get the corresponding strain in the steel level epsilon SC. We can get the corresponding steel level in epsilon SC. When we shall get epsilon SC, either from the curve or from the table that we have made it, from there we can find out the corresponding stress FSC. If we can get FSC, we can get the area of steel. So we can write down ASC equal to AST2 times 0.87 Fy. This is the tensile force, FSC minus FCC. You can further write down FSC minus FCC. FSC is the stress in steel minus FCC, because already we have taken that portion, so that's why you can deduct. In other way, our code says that no need of taking, you can simply ignore this FCC. So we can write down as AST 0.87 Fy divided by FSC. Okay. So we know AST now, and we can get ASC also. Okay. Now let us do at least 2 examples if we can manage it. Example 1, analysis of doubly reinforced beam. Given B equal to 300 millimeter, D 500, clear cover 25 millimeter, concrete M20, steel Fe415. Compression reinforcement (320 torr). tension reinforcement, five 25 torr. Let us draw the section. B, capital D, $320 525 okay. So this is your problem, and we have to find out the moment of resistance, at how much moment it can take. Number 1, MU1 due to concrete failure. MU1 equal to 0.138 FCK BD square equal to 0.138 multiplied by 20 times 300, that is the B. What about D? Let us calculate D. D equal to capital D minus clear cover minus 25 by 2, which comes as 462.5. The top and bottom reinforcement diameter are different, please note. 462.5 whole square equal to 1.7711 10 to the power 8 Newton millimeter, let us say 177 kilonewton meter. Okay. We shall find out the balanced steel. We shall get now the balanced steel. Number 2, compute balanced steel. Let us start from the beginning. 0.87 FYAST equal to 0.36 FCK BXU, or AST by BD equal to 0.36 by 0.87 FCK by FY times XU by D. PT AST times 100 divided by BD equal to, I can simply write down, 0.36 by 0.87 multiplied by FCK by FY multiplied by XU by D times 100 equal to 0.36 by 0.87 times 20 by 415 times 0.48 XU by D equal to 0.48 for Fe415. Okay. times 100 equals to 0.957%. So, balanced steel, that is 0.957%. We can write down AST1, let us continue, AST1 equal to PT by 100 times BD, 0.957 by 100 times 300 into 462.5, effective depth already we have computed, equal to 1327 millimeter square. Let us say 1328. What about area of steel? AST, that means tension reinforcement, equal to 5 I think I can write down. Okay. So 5 into pi by 4 25 whole square, which comes as 25 into pi divided by 4 into 5. So I can write down as 5 into 490. So if we write down, we can get little more, of course. AST2 equal to, I think I have taken little more. So 25 so I can write down here as instead of that 490.8. So so 490.8 say into 5, which is coming as 2454. Let us write down as 2454. Okay, write down as 2454. AST2 equal to 2454 minus 1328 equal to 1126. Mu2 will be equal to AST2 times 0.87 Fy times D minus D dash. D dash equal to clear cover plus, let us say 5 by 2, which comes as 25 plus, and the top 3 numbers of 20 diabar, 3 numbers of 20 diabar at the top. So 20 by 2, which comes as 35 millimeter. We can write down then Mu2 will be equal to 1126 times 0.87 into 415 multiplied by 462.5 minus 35, which comes as 1.737 8 equal to 173 kilonewton meter. Mu we can write down as mu1 plus mu2 equals 177 plus 173 equals 350 kilonewton meter. Okay. Number 3, compression steel. D dash equal to 25 clear cover plus 20 by 2 35 millimeter. D dash by D 35 by 462.5 equals 0.0756. We can also write down as this is D dash and the strain is 0.0035 XU. XU by D 0.48, XU equal to 0.48 times multiplied by D, which is 462.5, which comes as 222 millimeter. What about epsilon SC then? Epsilon SC will be, this is epsilon SC. Epsilon SC will be 0.0035 divided by 222 equal to epsilon SC divided by 222 minus 35, XU minus D. We can write down epsilon SC equal to 0.002948, 0.002948. So, if we can check, yes, we can check either from this table or we can go back to this curve, or we can go back to this curve. From here also we can directly get from this graph the corresponding stress. Instead of that, it is better to use this table, and in our case 0.002948, it means which is coming in this interval. So, we can find out the corresponding stress in compression steel. You can get that one in IS 456 also. It is in IS 456. SP16 is the design aid, that is special publication, but IS 456 that it will help you to design, but IS 456 is the actual code which you have to follow. So, we can write down epsilon SC 0.00276 strain, stress 351.0038 361. Therefore, epsilon SC computed 0.002948, FSC equal to 351 plus 361 minus 351. Let us make it multiplied by 0.02948 minus equals 352.8 Newton per square millimeter. mu2 equal to FSC ASC D minus D dash. FSC is the force in the compressive steel multiplied by the lever arm, which comes as 352.8 multiplied by ASC. What about ASC? ASC equal to 3 times pi by 4 20 square, which comes as 942 square millimeter. Okay, this is the area of steel in the compressive. 320 number of bars provided into 942 into 462.5 minus 35 equal to 1.42 into 10 to the power 8 Newton millimeter equals 142 kilonewton meter. So, we have got 142 kilonewton meter. mu1 how much? Moment of resistance due to concrete failure mu1 equal to 177 because this is a balanced section, and mu2 we have computed 142, mu 319, the sum of sum of these two 177 plus 142, which comes as 319 kilometer meter. One we have got two values. So, we have got two values 177 plus 173, 350. So, we can write down as say AMUT equal to 350 kilonewton meter. Let us say MUC 319 kilonewton meter. Therefore, moment of resistance of the section of the given section 319 kilonewton meter. That is what we have to find out. There is one more thing I should say, that why do we need to provide compression reinforcement. From the ductility point of view also we can say that we need that say steel in the compression side, particularly for say earthquake resistant structures. The compressive steel, adequate compression steel, it will help us to make it ductile. The next problem, let us solve one. I think we have time. Example 2, design of doubly reinforced section. Concrete given mu equal to 350 kilonewton meter. Concrete M20, steel Fe415, B, width of the beam 300 millimeter, capital D, overall depth 600 millimeter, clear cover 25 millimeter. Let us assume we shall use 25 millimeter dia bar. Assume 25 millimeter dia bar we shall provide. So, effective depth D equal to capital D minus clear cover minus half of dia equals 600 minus 25 by 2 comes as 562.5 millimeter. 562.5 millimeter. mu1, what is mu1 due to concrete failure? mu1 equal to 0.138 FCK BD square. mu1 equal to 0.138 FCK BD square due to concrete failure. It comes as 0.138 times 20 times 300 times 562.5 equals to 261.9 kilonewton meter, less than the applied moment 350 kilonewton meter. 261 due to concrete failure we are getting 261.9. That means the balanced moment we have to provide steel, compression steel. What about balanced steel? You can start with the same first principle. Instead of that, I am using PT equal to 19.82 FCK by Fy equals 19.82 times 20 by 415 comes as 0.955%. Or you can start doing the same thing from the first principle. Let us do, okay, I think it is better to give this one as a number 1. Okay, number 1 I can say this one as A and this one as say B. Okay, 1A, 1B. So, we are getting for the balanced section. Number 2, balanced steel 0.955%. Already we have computed. Therefore, AST1 area of steel equal to 0.955 by 100 times 300 times the effective depth, which comes as 1611 square millimeter. Moment to be taken by steel beam, or in other way you have to provide the reinforcement now, because we are doing it to separate way. One is that only isolated case of this singly reinforced section. Now we are adding reinforcement in the compression side and in the tension side. Both of them again will be in equilibrium, but since the stress level is different, that is why you will get two different steel area. So, mu2 equal to 350 minus, I can say 261.9 equals, this one I can consider as say 262. So, we can write down as 88 kilonewton meter. What about the area of steel 2? AST2 will be equal to mu2 divided by 0.87 Fy d minus d dash equal to 88 to 10 to the power 6 0.87415 562.5 minus 35, 562.5 minus 35, d dash equal to 25. Let us say again we shall provide the 20 millimeter dia bar at the top, which comes as 35 millimeter. We are assuming that we shall provide 20 millimeter dia bar at the top, like the previous one, 25 millimeter dia bar at the bottom and 25 millimeter dia bar at the top. We can provide the same, of course, which comes as 462 square millimeter. So, if we compute, then we shall get 462 square millimeter. What about the total tensile steel? Total tensile steel AST equal to AST1 plus AST2, 1611 plus 462 equals 2073 square millimeter. We know 462. 462 is the area of steel. What is the corresponding force? Let us say tensile force T2. Tensile force T2 equal to AST2 times 0.87 Fy equal to 462 times 0.87 into 415. This is the force. So, 462 times 0.87 times 415 comes as 166,805 Newton equal 166.805 kilonewton. This is the force. This force, if I say T2, we are talking the steel beam. CS, what is the distance between these two? d minus d dash. Okay. So T2 I know, because we are assuming that steel will reach the yield stress, and that is why it is simple. We can immediately calculate the AST2, and since we have already computed AST2, so we can find out the tensile force. Already we have done the balanced part, that means concrete failure and tensile 1, AST1 and the concrete failure, that already it is balanced, we have done it and it is in equilibrium. Now we are providing the tensile reinforcement, which is AST2. So corresponding force T2 166.805 kN in this problem. We have to provide the reinforcement in the compression side such a way so that it will be in equilibrium. So we have to find out that CS should be equal to T2, but the strain at this level is different than the strain at this level, because in this case the strain is coming from the top fiber concrete failure, that is 0.0035. So the compression side, the steel will never reach the yield stress 0.87 Fy, it will never reach the yield stress. We shall find out that yield stress getting the strain at that level and the corresponding stress. So we have to find out the strain and stress, but your force will be equal to 166.805. In other way I can say ASC will be equal to, say, T2 by FSC, or in other way CS by FSC, but we do not know FSC. At this moment we do not know FSC, but we know the strain, and from that strain we can get the corresponding stress, and if we can find out the stress we can get the ASC. So number 6, stress in compression steel. So XU 0.0035, we are assuming we shall provide 20 millimeter dia bar. So clear cover 25 plus diameter 20 millimeter diameter equals 35 millimeter. This is your that D dash. XU by D 0.48, XU equal to 0.48 times 562.5, 270 millimeter. Epsilon SC equal to 0.0035, which will be always less than this 0.0035, minus 35 equal to 0.00304. From the table again we are getting the same interval 0.00276, which comes as 351 stress, strain 0.0038, 361 from the table, the one which we have given in the last class, last lecture. So FSC equal to 351 plus 361, let us make it in detail, 0.00304 minus 0.00276 divided by 0.0038 minus 0.00276 equals 353.7 Newton per square millimeter. So, we have got FSC, we can calculate ASC. ASC equal to, in other way I can write down ASC equal to AST2 times 0.87 FY divided by FSC equal to 462 into 0.87415 divided by 353.7 equals 471.6 square millimeter. Area of steel AST equal to 2073 square millimeter. ASC equal to, let us say, 471 square millimeter. So, this is your design, and we can finally provide the reinforcement also, that it may come again that 525 and 220 something like that can come. So, you can provide the actual reinforcement also, you can provide. So, we have done two problems, one that analysis of beam and the other one the design of doubly reinforced section. We shall do in the next class, since we have time little bit, we shall do the design of flanged section or flanged beam. As I have mentioned, this is your slab and beam. At the support, at the end, it generally comes, we can call it as inverted L. We take, whenever it bends, we take certain portion from both sides, or from this side we take, that is the called flange. You can say that you say wave type of thing, T-beam like this. Now, what we shall do, we shall take the width of the flange also, not only wave. So far we have done the rectangular section. So, we shall take this portion also, that wave as well as the flange. For this case, we shall take certain portion up to this. What we shall do, we have to find out, say BW, let us say certain dimension BW, width of the wave, overall depth, DF, depth of the flange, width of the flange, and depth of the wave. Depth of the wave we can get. What we have to do, we have to find out we can do the design as well as we can do the analysis. Moment of resistance we can find out for these sections. Here what happened, only thing I shall mention today, there could be three different cases. Depending on the stress block, this is your stress block, what we can get, this is from here to here that constant. It is possible the whole stress block within flange, it is possible that whole stress block within flange, that could be one case. The other case could be the slab portion of the flange within this zone. That means we are having the constant stress in the whole portion. But other alternative could be third one possible, that we are having in between here. So, which is the most difficult one? The first one, it is easier, that it is nothing but the simple the rectangular section, only instead of using B we shall use the BF. The other case also we shall have two parts, one part is the rectangular portion, other part is the flange portion, but it is having constant stress, so we can get the force easily. But the third part where you are having somewhere in between the flange, so then it is a difficult portion, that how much will be the force, that also we can find out. So these are the three different cases, and that we shall continue in the next class. Okay. So thank you.